Hi, I am Vaibhav Bedi from Bhopal. In the previous video of resonance, we covered some basic concepts of resonance and hyperconjugation. Now, in this video, I'm going to explain resonance. I'm going to explain more about resonance, that how we can uh, find the structures contributing to different resonance. Now, let us come to the concept of resonance hybrid. See, there is a molecule which have a carbocation at its end, and we have discussed that if there is a carbocation at its end, there should be single bond, then a double bond or a triple bond. So this is the basic concept of the resonance. This double bond will shift here and the second contributing structure will be this. So these are two structures which are contributing to the same molecule. It means that if we mix those structures, or if we consider that these are simultaneously happening, then our third structure will be like this, and this will be the most stable structure, because we have discussed that in resonance the energy is released out of the system. So the potential energy of this molecule will be the lowest, so its stability will be the most. Now, we cannot apply Le-Chatelier principle to a resonating structure. That is simply because the resonating structures are not real one. These are only hypothetical structures. It is because of our ease. We need to understand the concept, that how the reactions are happening. Therefore, we have developed a method which is known as resonance, that like this it could be happening. So we are explaining our chemical reactions through this. So it's not a real phenomenon, we have to remember this, but though it explains our chemical reactions. Now let us come to some of the examples of resonance. Like we have a carbocation here. It is a carbocation, then single bond, then there is a double bond, so it will shift here. This will become this structure, and this will again becomes this structure. So in total, we have three structures of this molecule. Again, coming to the second molecule, now we have a ring structure, there is a carbocation. Now, here, there is a carbocation, there is a single bond in both the directions, and in both the directions we have a double bond as well. So, first of all, let us consider this right one. If we do this right one, this bond will shift here and carbocation will shift here. Again, this bond will shift here and this carbocation will become here. But if we consider this left one, then there will be a different structure to this. So in total we have 5 structures. So we have to remember that whenever we are doing resonance, we have to take care that all the double bonds should participate in the resonance. So though it is known as bidirectional resonance or polydirectional resonance, we will come to this little further. Okay, now we are come to the concept of unidirectional resonance. Now here in this molecule we have a carbocation at one end and all the double bond are at one end. So what will happen is this will shift there, this second one will shift there, this third one will shift there. So the electron flow is always in one direction. The electron flow is always in one direction, therefore the energy will not be scattered. Means the energy flow will be only in one directional, and that is more stable. But in polydirectional resonance, like in this, we have energy scattering from all the ends, therefore it is not that stable. So unidirectional resonance, sorry, so in unidirectional resonance, what we do is that from all the ends, the energy is scattered or the electrons are coming. Therefore, these are not that stable. So unidirectional resonance is more stable than polydirectional resonance. Now let us do some exercise. Let us find out in this molecule. Let us find out in this molecule that which are the double bonds which are contributing in the resonance. We have learned a concept that carbocation, single bond and double bond. So carbocation, single bond, double bond. So check. So this will perform. Carbocation, single bond, double bond. So this will also perform. Carbocation, single bond, double bond, single bond, double bond. So this will also perform. So there are only three of the double bonds. There are only three of the double bonds which are participating in the resonance, and these are not. So the bonds or anything, the bonds or the lone pair which are participating in a resonance, we call them delocalized double bond. And these are the localized double bond, means they are located at one point only. Like this, so see here, only these three will be delocalized. Now coming to one more example which will state that how we can apply our concept. Now here it is, carbon double bond, carbon single bond, this positive charge. So we may make the mistake that we shift this double bond here and we make the nitrogen pentavalent. But as we know, as per the concept of chemical bonding, that nitrogen cannot be pentavalent. Therefore this structure we cannot make. Okay, so the ultimate condition is that if we have a negative charge or a positive charge or a radical or anything which can do resonance, which we have discussed in our previous video, that should be, this sequence should be followed, that this entity should be there, then next to it should be a single bond, and then there could be a double bond or triple bond. Like in this we have a carbocation, positive, single double. So if this series is being continued, we can do resonance. Okay, now coming to our next slide. Now here is also an example of our mistake which we may encounter, that there is a positive charge, there is a double bond, positive single double. But if we will shift this double bond, or if we shift this pi bond of oxygen, then there will be O positive created, which is not suited, because oxygen is highly electronegative. It cannot, it can take positive charge, but it can take positive charge but not in all the cases, because here its octet is not complete. So what I repeat is, if the oxygen's octet is complete, like in H3O positive ion, the positive charge is on oxygen, but there its octet is complete. Therefore we can make positive charge on oxygen only if its octet is complete. But here we can see the octet is not complete, therefore this is wrong. Okay, now there is again an example of localized positive charge. Now here N positive is there, and there is a benzene ring. Now if we will shift this double bond here, then the nitrogen will become pentavalent. That is not possible here. But in this case SH2 positive is there, because sulfur has a d orbital, it can expand its octet. It can be pentavalent, it can be hexavalent as well. Therefore if I will shift this double bond there, then it will perform resonance. So here resonance is there, but it is only in the ring. But here in this case the resonance is in the ring as well as the SH2 plus. Okay, now we have come to the point of resonance due to lone pair. Okay, now there is a double bond, then single bond, then there is a lone pair which can be shifted. So we have always read, or I have taught you that there should be an entity which can contribute to resonance, single bond and double bond. So we are following this only. Now this will contribute to this structure. See, oxygen has given its lone pair to the single bond, and the negative charge is on the last carbon. Now here oxygen can contain positive charge because here the octet is complete, therefore it can take part in resonance. But the lone pair which is localized, means there are two lone pairs of oxygen, one would participate in a resonance and one would be there, means it will be localized, it will not participate in the resonance. Therefore if we want to guess the hybridization of this part, then we need to take account of the localized lone pair. We will not consider the delocalized lone pair, but the localized lone pair will give its hybridization. So we may tend to say that here the hybridization must be sp3, but if we apply the concept of resonance, the hybridization comes out to be sp2. Okay, now here there is a further example of resonance, and see, there is NH2. This can donate its electron to the benzene, and this whole thing follows, and I think we should be able to do this easily now. Okay, coming to our next slide. Now I want to discuss some of the cases in which a lone pair is not participating in the resonance. So here there is a ring which is more likely a benzene ring, but here is a nitrogen at its end. Okay, now we may tend to say that this nitrogen's lone pair will uh, perform resonance, but if we perform resonance by nitrogen, this thing becomes sp hybridized, and sp we know it is linear, but in a ring structure, if one part is linear, the ring cannot. But if we apply resonance here, the ring cannot be formed because this thing will have to be linear and not something of 120 degree or 90 degree. Okay, so uh, now let us do some exercise. Let us find out the localized and delocalized lone pairs, because it will help in further continuing our application to chemical reactions. Now say this is a molecule. And see, this is localized lone pair because it does not have any single bond, double bond nearby it. This lone pair on nitrogen will definitely be in resonance because there is nitrogen single bond and double bond. Now these both will be localized, because if I shift this lone pair to this single bond, then there will be positive charge on oxygen, and this oxygen will have incomplete octet, and this is also obviously that delocalized charge. Okay, now this is the thing which I have discussed already, that positive charge on oxygen can only come when its octet is complete. Okay, now let us consider this example. Now this will be localized because there is not any single double bond nearby. There is a single bond double bond nearby, and its hybridization will be such that it will not affect the ring. This will be also delocalized, and this will be also delocalized. Okay, now coming to this molecule, there is oxygen single bond and a triple bond, so our criteria for resonance is fulfilled, and only one of the lone pair will shift its lone pair and one will be delocalized. So one will be delocalized and one will be localized. Now resonance due to polar pi bond, though we have discussed this thing in previous class as well, but we need to sharpen our skill because these things are very hard to find in a question. Okay, so there is a carbon double bond oxygen. So it is a polar thing because oxygen is more electronegative than carbon, so it will attract electron more. So we can assume that there is negative charge on oxygen and positive charge on carbon, so a carbocation is created, and if we will find carbocation, then single bond and then a double bond, so we can apply resonance. So like in this case, we have carbocation, single bond and a double bond, so we will apply the resonance as in same in this case, that carbon double bond. Okay, now I will discuss in the next video rule for stability of resonating structures. So first of all, let's discuss that why we need this. The most stable structure of all the resonating contributors will show most of the properties in a chemical reaction. Therefore, if we need to understand a chemical reaction, that what actually is happening, we need to look at the resonance hybrid, which is the resonating structure, which is the most stable out of the structures which we have made, and we can focus on that structure only. Thank you.